yesterday we had a rain day, which I'm kind of like, okay, but we had a rain day. I Yep, snow, sleet, all that good stuff. I came and worked for 4 hours in the morning, including doing your video lecture, which honestly was not, I don't know who said that timer, was honestly not the most efficient video in the world because there was like so much happening, like buzzers going off, and I was like, what in the world? But you guys learned yesterday, according to schedule, Le Chatelier's principle. And Le Chatelier's principle was the follow-up to understanding reversible reactions and how reactions, some reactions, not all, can go forwards and backwards. They can do and undo themselves, okay? Equilibrium is a status, and for chemistry, it's always dynamic. It's always actively something's changing that creates a pseudo-static result. Constant reactant concentration, constant product concentration, because the rate of the forward is equal to the rate of the reactant, or the reverse. Sorry, the reverse. That's why we follow kinetics. We do equilibrium after kinetics, okay? Because it is technically an application of rate, all right? But it's obviously its own significant topic. And so we talked about Le Chatelier's principle. Could anyone please tell me, and then I'll talk about unit 6 quickly. Could anyone please tell me how does, according to Le Chatelier's principle, I shorthand it as LCP, how does a reaction, 1 second. How does a system respond to, for example, A, an increase in product? How, according to Le Chatelier's principle, will the reaction respond?
It shifts towards the reactants.
It will shift toward the reactants because, and I should scroll down to the part of our notes that we actually are talking about, unit 7. It will shift toward the reactants because you are trying to undo the additional weight in concentration on the product side. So I did a really sketchy little like balance scale thing that did not turn out very great, but that's okay. Where if you think of it like a teeter-totter, I don't know if you guys ever played in a park before, because I don't know what you guys grew up doing. Okay. But if you think of a teeter-totter and there's a fulcrum, right? If you have a really like a middle school kid versus like a third grader, right? What you'll see is that you want to eventually pile up a bunch of third graders, right, to even out the scale of the larger middle schooler, theoretically. So if you have an increase in concentration on the product side, you're going to want to somehow alleviate that. And the Le Chatelier's principle is always about the alleviation methods, not the immediate result. It's about how do we undo it, okay? How do we undo that change? And so what's going to happen is the equilibrium position is going to change. The fulcrum, you might change the fulcrum point in terms of where your rate of forward versus rate of reverse is established to create an equal stoichiometrically aligned production of reactant versus products. Okay? Yes.
So, but for that analogy, wouldn't you be more realistic to chop up the middle schooler and turn it into a bunch of third graders?
That was very violent.
Are you really gonna criticize people's violence?
I am not that violent.
The one that talked about bringing the chicken head.
That is a cooking method. How do you think they got the chickens before?
But still, like. Still
Anyway, I didn't have to do it with a human. I did it with an ugly little creature, a chicken. They're dispensable. Chickens I've seen. Okay. So we would shift toward the reactant. Thank you. So how about B? What if I add heat, temperature to an exothermic reaction? For an exothermic reaction, heat's treated like a product. So it'd be like adding product. How would my reaction shift in response to establish a new equilibrium? Yes. It would shift toward the reactant because I have to undo that additional heat product. Okay. Finally, for a gas-based reaction with different mole particle amount, on reactant versus product, because remember, for volume change or pressure change to have any effect on a gas-based reaction, you have to have different moles of particles cumulatively on the reactant versus the product side. What would happen if I increase the pressure? how would it shift? It would shift to which side if I increase pressure and I want to undo that? Parikh. It would shift to the side with the less amount of moles because it's just kind of like grouping up the particles until, yeah, bigger clumps, basically. Okay, to reduce pressure because there's less particles colliding. Yes, even if they're bigger.
What do you mean by shift to the other side if you have a product to react?
So when I say shift to the side, it means the reaction equilibrium position will shift more toward the products where the rate, products where the rate of the forward is more favored than the rate of the reverse.
Okay, so you're making more reactants
Mm-hmm.
in a certain ratio than you are making products.
Well, if you're going to shift toward the reactants, you're making more reactants than you are products. You're going to shift toward the product. You're going to make more product to reactants to find a new position of equilibrium where there's a new balance between.
So you increase the rate of reaction like the opposite.
You increase the rate of reaction of the direction you want to go.
Okay.
Yeah. And the other reaction will kind of slow down to even out the addition or subtraction of something. Yes. Yes.
In regards to like adding molecules to shift the equilibrium point, why exactly does that shift the equilibrium point after it all stabilizes instead of just increasing the rate of both reactions?
Because if you increase the rate of both reaction, that means the concentrations will remain constant. So you'll still have a greater amount of uneven that doesn't align with the stoichiometric relationship of one specific species that you don't want. So you want to use up that species. And that means you're going to have to progress one direction and slow down the other, causing a different placement for where equilibrium is found.
Wouldn't you also just be able to like not increase the rate of both reactions at the same time?
Would you also what?
Well, wouldn't like the fact that you can't just increase the rate of both reactions at the same time take precedent over that?
No, I don't think so. Are you understanding his question, Charlie?
I wasn't really listening. Sorry, what was?
That's okay. That's totally fair. You were saying something, wouldn't you be able to?
Well, someone asked like, what would happen if we increase the rate of both?
Well, then nothing would happen.
But you can't increase the rate of both.
Yes, you can. It's a catalyst.
Okay.
The catalyst increases the direction, the process for both directions, because it just makes the overall process faster. But what I am talking about is this stress causes one direction to be favored more than the other to undo it. Yes.
But like, let's just assume that we have more of one reaction and then
More of one reactant.
reactants than the products.
Okay.
Why can't you have it so that one reaction just takes place a lot more? The reaction.
Well, that is what's happening.
But then it eventually stabilizes out once the ratios are roughly what they should be.
Yes, but it's forever, but it is shifted permanently because now it will stabilize, but the position that it's found in will now be different.
Is that just because it takes energy to do those initial reactions?
No, it's not about energy at this point. It's about using up product or using up reactant. It's about the relative ratio between product and reactant. That's what equilibrium is. It's the relative ratio between product and reactant indicated or achieved through the rate of the forward equaling the rate of the reverse, theoretically. But if you create a stress, your concentration ratios are different, which means your equilibrium position is different.
But given two substances that have a certain ratio that they like to correspond to, can you just convert more of the reactants to the products? And then
That is what's happening. That's exactly what's happening.
The stress will change it temporarily, and then it will act to return to that ratio.
So the
But
equilibrium- sorry, go ahead.
But the equilibrium position in terms of where the rate of the forward and rate reverse has established a new location. The rate of the forward has now shifted in a way to accommodate, and the rate of the reverse has also shifted to accommodate.
It shifts temporarily, and then once it reaches that original equilibrium point, the rates will. If the rates will shift in order to alleviate the stress, and then they will.
And that's why your equilibrium shifts.
So just to be clear, the relative rates will shift back to their original position. in this-
Well, the relative rates will shift back to whatever maintains the new equilibrium found with the addition or subtraction.
Which would be the same thing as.
Yes. Yes, it would be the same thing.
Yeah. But the equilibrium, we say the equilibrium position has shifted, and it's going to become a lot more clear in today's topic. We're going to add numbers to it to show you how that happens. Okay. Okay. So, out of curiosity, just raise your hand. How many of you guys watched the video or at least filled out the notes on Le Chatelier's principle last night? Okay. Raise your hand if you didn't watch the AP, one of the AP problems, either Monday night's AP problem or yesterday night's AP problem. Did anyone not watch either AP problems? Like both Monday and Tuesday night, they skipped the AP problem walkthrough. Is there anyone who did that? You didn't do AP problem walkthrough Monday or Tuesday? Raise your hand, please. Yep, I have to do homework checks. So Monday was unit 6. Yesterday was unit 7. So Hannah, Jaden, Sophie, Ava. Okay, too many people. Hold on. Hannah, Jaden, Sophie. Hold on, Hannah. Wait, I don't have a Hannah in this class. Who am I saying was Hannah? Oh, Hannah Weber. Hannah, Jaden, Sophie. Okay, so I have people that are going to have to submit proof of completion for AP problems. Camilla, Jaden, Sophie, Olivia, Hannah, and who else? Someone else raise your hand. Ethan and Ava and Nathan. Ethan and Ava and Nathan. They just got to submit proof that they've done AP problems. Remember, I started doing AP problem walkthrough videos. All right, so we're going to kind of go backwards for a hot second because of our missed day. And we're going to look at the unit 6 calorimetry problem that I asked you guys to do. So we're going to pick up with Le Chatelier's principle in a second on equilibrium. But I want to quickly revert back to unit 6 and just see what you guys got for problems. Sample problem page 13 and 15. So sorry for the back and forth. This is why rain days are awful. Missing a school day is not good for AP kids. It messes you guys up really bad in curriculum.
Well, we did our work.
So
Already like cut everything.
I don't think they took AP students into their calculation of like.
Yeah, the rain was like, but these AP Chem kids, man.
yeah.
Well, I think.
So for this one, you should have, I gave you a tip and I was like, hey, you're gonna have to recognize that this is a multiple step Q calculation. So for the first section, you had to use Q equals MCAT, thermodynamics unit 6 problem review that we're moving to today because we got school canceled yesterday, or the rain did. Okay. This first section, you should have used Q equals MCAT to figure out how much heat was flowed into the system, because we're going from a liquid to a gas, how much heat was absorbed by the water to even get to boiling point. So you should have gotten Q equals 50 times 4.184. You do need to memorize the specific heat capacity of water times the change in temp, 100 minus 25, 75 degrees Celsius.
4.18. 0.
The graph, the chart page about is 4.18.
Okay, 4.18. Some constants do 4.184. So 50 times 4.180 times 75. And you should have gotten that the heat for this portion, the incline, right? This portion, the incline of this process was 15,675 joules. Okay, then you had to do the heat during the plateau portion, where how much heat was being used to even break the IMFs. This is where we have this adjusted Q calculation where you don't have a change in temp, but you do have heat that goes with the process of vaporization. So you do mass times heat of vaporization, okay? And so what you would say is 50 times the heat of vaporization for water is 2,250 joules per gram, okay? That you would have had to look up, and I think I put it possibly in the notes, but I might have gotten rid of it because it's not a memory number you have to memorize. It would be given to you, okay? It's giving you a total of, for this portion of the transformation, the latent flat zoned plateau portion, you would have 112,500 joules. And then for the final portion where you've thoroughly, okay, turned everything to steam, now you're just increasing the temperature of the steam particles. You're just increasing the kinetic energy of the steam particles. You go back to Q equals MCAT, and it becomes 50 times heat capacity of steamed gaseous water, which is 2.01 times the temperature change from 100 to 120, 20 degrees Celsius positive, and you would get a value of 2010 joules. And then what you would say is for this entire process to occur, okay, you would add up everything. So the sum would end up being 130 kilojoules to the correct sig figs. Okay. So hopefully that's what you got. It's pretty basic math button pushing. We call it plug and chug. You plug in the values to a known equation, you chug out the calculations, you plant the answer, circle it. Please remember that whatever you circle in your calculations as the answer, the AP will grade you off of that circle. Okay, so I know a lot of you guys will sometimes like have the answers in the corner, but then you like boxed a different like calculation because you doubted yourself. The AP will grade you on the one that you boxed, okay, that you identify as the answer. And if you don't identify any as the answer, that is a big Russian roulette moment. You do not know how they will take that. Yes.
I was just wondering what part they would grade.
Oh, yeah. If you didn't box any, I don't know. It'd be the great. I mean,
If you did it right and then you did it wrong, then maybe there was like they might not grade it as right.
yeah, because if you,
chose to do incorrectly afterwards,
it means you didn't understand the concept. Yeah. Okay, so that was the one I wanted you to do, and I wanted you to do one more, where you're determining molar enthalpy. So for this one, what you should have noticed is first and foremost, we're using Baum calorimetry, which again, the calculations don't change with the Baum calorimeter. It's just a different instrumental device. It's just a metal-based device that's a little bit more accurate than styrofoam. Okay. And you see an increase by 6.12 Kelvin. So quick note, notice that when you change from Kelvin to Celsius, the scale of change is consistent. Like 1 Kelvin change is 1 degree of Celsius change. Okay. Because you only are transforming through a constant addition, not like a mathematical like multiplication process. Okay. So you know then that the change in temperature was positive 6.12 degrees Celsius as well. You are given the heat capacity of the system. What is the molar heat of decomposition? Molar heat just means what is this in kilojoules per mole? That's all I'm wondering. So what you should have done is you should have done the following process where you turned, okay, grams, 1 gram. Okay, Q equals 1 gram times heat capacity. And you have heat capacity in kilojoules per gram per degrees. You can turn that into joules initially, or you can leave it as kilojoules because you want it eventually as kilojoules. So 1.23 kilojoules per gram degrees Celsius times change in temp 6.12 degrees Celsius. And what you should have gotten is you got a value of Q. And did anyone get the value of Q? 7.53 kilojoules is what you got. Now I want per mole. So I have 1 gram of NH4NO3. So I need to figure out how many moles of NH4NO3 were in the sample, because this amount is specific to the 1 gram. 1 gram of NH4NO3 times the molar mass to get it into moles. So what was the mole amount of NH4NO3 in the sample? The molar mass of NH4NO3. Yes.
Sorry, question. Why do we convert this to Celsius?
Because that's what the Q equals MCAT equation is, because your constant specific heat capacity is per degree Celsius. But the scale of change between degree Celsius and degree Kelvin is still the same. A 1 Kelvin change is a 1 degree Celsius change. Does anyone know sodium nitrate's molar mass? 2.0434? 80.0434. So what is 1 divided by 80.0434?
1/8. Would it not be, you have
Uh-oh.
you have kilojoules.
This
for
is gonna be a
1
problem.
gram, And then you want, yeah, one.
So it's 1 gram. So I want the number of moles of NH4NO3, and then I'm going to divide the kilojoules by that mole amount that was present in the calorimetry that we just did. So what was the mole amount in 1 gram of NH4NO3? Using molar mass that you just told me.
Would that not be 7.53 times?
0. What'd you say?
Well, I'm sorry.
Okay, then you divide this by 0.013 moles and you get kilojoules per mole, which it's okay. And what you should have gone is when you divide that in Elise, what'd you get? 7.53 divided by 0.0153. 7 kilojoules per mole. Okay. Well,
Why couldn't you just multiply 7.53 by 80.0434? Starting in kilojoules over 1 gram, and then you go.
I mean, you could have. I'm just
0.0434
showing the,
grams per mole.
you can do that. I'm just showing that this is the conceptual understanding of why you would do that. You need to get to per mole. So you got to figure out how many moles of sample were present in that 1 gram. Because that heat release or that heat absorption, I guess I should say, is unique to that mass amount. But I want to standardize it to the mole. So I got to scale accordingly. Does that make sense? Okay, so that's the end of Unit 6. Sorry for jumping back and forth between Unit 7 and Unit 6. Let's go back to Unit 7 and get clarity on what does it really mean to define an equilibrium position. And this is where a math is going to come back into place, okay? And where that capital K is now very important to us, that we use for substitution for RDS. When the RDS of a reaction, multi-step reaction is the second step, that's where we use this. So, and remind me to constantly be plugging in my Apple Pencil. All right, so back to Unit 7 notes. So we're done with Unit 6. Despite the mess of the rain day, we did calorimetry. There's an AB problem out there for you. It's calorimetry problems are plug and chug, baby. That's like, you can bank on them being plug and chug. It's really nice. Now this Unit 7, where we're talking about reversible reactions and equilibrium, and basically identifying the points of balance and how reactions respond when unbalanced, okay, leads us to a new expression known as what we call the equilibrium or K constant expression. All right. And so what we have is our equilibrium expression is a formula. I'll zoom in, is a formula, okay, for finding or determining the equilibrium constant, which is a numerical value that represents where equilibrium is found relative to the concentrations of product versus reactant. Capital K, this is capital K. Formula for finding equilibrium constant in terms of the reactant, okay, the ratio of product concentration over reactant concentration. Okay, at equilibrium. So it is specifically defining the moment, the ratio between product and reactant when the reaction is at the status of equilibrium, not shifting, not in the process of getting to, but at. So just for a little derivation's sake, if you're like wondering how we're going to get this equation, is if you recognize that we are relating the rate of the forward to the rate of the reverse, and we say that for a reaction, okay, to be at equilibrium, the rate of the forward has to equal the rate of the reverse. So if we're given this reaction, rate law, this is Unit 5, little r, little k, okay, this is Unit 5. If we're given this reaction of forward and reverse, okay, this is the reverse rate, this is the forward, and we set them equal to each other as according to the definition of equilibrium, all right, we would say that little r, okay, little rf has to equal little rr, and little rf equals little kf times H2 concentration, I2 concentration, both first order. Okay. And it's got to equal whatever's equal to little r, right? So what we would say is then K little r for reverse, the rate constant for the reverse process, times the HI, okay, concentration of the relative reactant, second order. So we set them equal to each other because that, according to the definition of, is what equilibrium really is. Okay, so then what we do is, then what we do is we say, okay, well, if I were to compare the rate of forward product making versus reverse, I would say that little k, rate constant for the forward direction, all over the rate constant for the reverse direction, is going to also reveal the relationship between the product making concentration and the reactant favored or making concentration. So what I do is I do HI2 divided by, I just rearrange the equation, H2 times I2. And then what I get is that together this entire ratio is equal to the capital K constant for at equilibrium. What is the ratio between my product and reactant? That is going to give me a constant value that represents the status via concentration of my equation at equilibrium. And that's actually how we derive KEQ from unit 5 one direction rates. Okay, based on the concept that rate forward must equal rate reverse at equilibrium. And so we just manipulated the rate law equations to get there. Okay, so then what we get is we get this generic equation for a capital KEQ, equilibrium constant, is equal to the concentration of your product species raised to their stoichiometric coefficient times the concentration of your reactant species raised to their respective stoichiometric coefficient. And that is equal to products all over reactants. And this value, this numerical value, represents, all right, or indicates, represents, like indicates the equilibrium position. Okay, of a reversible reaction. Are we favored toward the products or are we favored more to the reactants? Okay, and it also should be noted that this actually has no units. It's just a number. All right. It's very relative. Basically, if we say it's greater than 1, you're favoring products. If it's less than 1, you're not. Absolutely outstanding.
Almost like fractions.
It is indeed, dare I say, a fraction. Okay, so yes.
I'm sorry, this is unrelated, but I think there's 47 days until the it's listed on the sheet and the agenda.
Is it 47?
I think so.
Well, we'll leave it 40 until it reaches 40.
Yeah.
Okay.
A little bit of extra heart attack.
Okay, so couple things about this value is, or determining this representative value, is that one, you got to start with the balanced chemical equation. You can't do any of this without it because you got to have your coefficients. So start with balanced chemical reaction. And then 2, please make sure that when you set this up, you do not include units in the final answer. And of course, you correctly identify product and reactant. Sounds silly, okay? But if you flip it, you do the inverse of the reaction. So be careful not to flip. So make sure you put correctly identify products, okay, as numerator. Silly mistakes are what kill people, okay? Don't make silly mistakes. So one thing about KEQ that you should know is if any of your chemical species are solids or liquids, Okay, if any of your chemical species are solids or liquids, we do not actually include it. We say that they are equivalent to a value of 1, so it acts like a constant. Now, quick note, I am not saying though aqueous. So if your species is aqueous, we actually do count it.
But it's solid.
No, if it's aqueous, it's an ion.
Okay, that's fair.
So, quick note, we do
It's a solid
include
ion.
aqueous species. We just don't include pure liquid species. So like pure water liquid, which again, you never write water aqueous. Don't do that. Water liquid, pure mercury liquid, a metal liquid, gold liquefied. Like none of that would be included in your KEQ. You would just not even write it into the expression because it would act like a 1.
We do include, but I guess-
We do include aqueous. We would never include solid or liquids. Yes.
What do you mean by acts like a one?
In terms of its concentration change, it doesn't change.
1 times the
Right.
concentration times 1.
Yeah.
You don't really have to consider it in like the.
Yeah. That's a nice color on you, Charlie.
In the calculation, because if you have a solid or a liquid,
So the only
how
time
much
we-
you have doesn't really change the rate that the reaction is receiving at. The
Yeah.
concentration does change the rate a lot, where the density of the gas in the space would change the rate.
The only time we include the concentration is if it's aqueous.
Yep. So we do include the concentration of solutes, okay, which usually end up being ionic compounds, right? In aqueous solutions. So there's a lot of that in life, a lot of true enoughs. Okay. So for this one, go ahead and let's do this one together. So for the following equation, we have 0.19 moles of NO2, 0.64 moles of N2O4 are found at equilibrium. You must have the assumption that you're at equilibrium. You cannot write KEQ if you are not at equilibrium. Okay. In a 250 milliliter flask at 92. Okay. So what is the K equilibrium constant? Okay. The K constant, capital K. So KEQ is going to equal the concentration of product raised to its stoichiometric coefficient, which is 1, all over reactant, NO2, raised to its stoichiometric coefficient of 2. So then what we do is we say, well, the concentration that we've been given is, for our product, we have 0.64 moles per 250 milliliters. So that's 0.25 liters. Okay, that would give us the concentration of our product all over 0.019 moles over 0.25 liters, right? And we would square that value and you would get that our KEQ constant, no units, is 4.4, which means the product side or direction, the forward direction, forward reaction is favored. The equilibrium finds its position, if we look at the fulcrum, as finding balance closer toward the products and the reactants.
Wouldn't we be able to discern that just by looking at the vector of both gases and one of them has a significantly higher stoichiometric concentration on the reaction side?
I mean, you could, but if you didn't, if you had more than one species, that would make it more complicated. So, what does the magnitude mean then exactly?
So in that case, there is more.
It means in that case, there is more, at equilibrium, there is more product concentration present than reactant concentration.
So that when a reaction side be favored to balance it out.
No, because this is where equilibrium is established. Is in favor of the product. That's where the fulcrum has to be balanced. Okay.
But what you're saying is correct. The fulcrum is placed in that specific place to balance it.
So. Okay, so don't worry, Kian, you're still my number 1. Okay, so the bigger the KEQ, I love how he had to like whisper that to me. Like the bigger the KEQ, okay, the further the reaction progresses. The further the reaction progresses forward. Yes. Which, by the way, means you're going to have increased percent yield of product. Okay. So what we say is when we have a larger KEQ, we say that the reaction goes nearly to completion. Completion being in the direction of the forward, nearly to completion at equilibrium. At equilibrium, we are basically just producing product with a little bit of undoing. That's where the balance is found. That's where the establishment of the rate of the forward has to equal the rate of the reverse when we have slightly more product being made. Okay.
So if we want to maximize the amount of products being made, for example,
we want to bump up our KEQ somehow. So we want to speed up the rate unit 5 rate understanding that way in the forward direction. So you're going to notice a lot of overlap between unit 5 principles and unit 7. But remember, unit 7 is equilibrium ratio. Unit 5, K constants and all of that talk is in one direction. Just generally speaking, is this going to go faster this way? And that's all you care about. This unit's about, okay, I have things going forward and backwards. How do I figure out the balance between the two? Mashed potato. Yes. Sky.
So when you say nearly to completion, is that essentially like an asymptote? Like it never.
Yeah, essentially. So like what it's like saying is it's like if you drew this, you're in your equilibrium, your reaction like equation would look like a giant arrow forward and like a little arrow backwards because it's just a little bit is going reverse. Yes.
I was just gonna say, like, this guy, it's not really like an asymptote as in it gets closer and closer to truly being complete. It just means that that point where the rates are balanced, where it reaches equilibrium, is very close to completed products.
Yeah. So I don't know. I kind of like the asymptote idea, but yeah. Malcolm.
so let's say we had an exothermic reaction that was reversible and we wanted to have the highest possible percent yield.
Yes.
We wanted to affect it by increasing or decreasing the temperature. Will we increase the temperature or decrease the temperature?
We would want to decrease the temperature. But there's the catch with those types of reactions. Exothermic and endothermic reactions, if you mess with temperature, you also mess with the collision frequency. So you might not want to actually mess with temperature necessarily, and you might want to do another way.
Yeah, because then you would reduce the speed of your reaction, but you would
favor the product.
Yeah,
you would favor the product in a slower way.
Yeah.
Exactly. Yes.
What exactly does the equilibrium constant?
It is the ratio between product and reactant. That is the equilibrium constant at equilibrium.
Isn't that given by the original stoichiometric ratio though? As in, isn't that all be specified?
But it's the key is at equilibrium. That's the key. It's not at any point in the reaction. I'm going to introduce you to that. It's once I found equilibrium, what is the concentrations? Maggie, head up. So some limits to predicting equilibrium position from KEQ. Okay, it is impossible to identify. Did someone say you sure about that? To identify. I can't spell it.
All right, sound it out.
Okay, the exact equilibrium. Based on KEQ magnitude alone. Well, if I just gave you the number 7, that doesn't tell you very much. You just know that you have your products in a ratio 7 times greater than your reactant.
Nice.
Right? So it gives you a general idea, but it doesn't tell you the exact unless you had all the data beforehand. But the KEQ value alone just gives you a general idea of favor, which side's more favored. It doesn't tell you exactly the scenario unless you're given the data beforehand. Yes.
This is in regards to the rate law, it's like limiting reactions one, where we have to do the split step and fast step, unit 5. How exactly do we determine KEQ in that scenario if we're treating it like a constant?
For unit 5, you You didn't. You just used it as an algebraic manipulation. You didn't actually have any values in it.
So is KQ, do we ever have to determine KQ in that context?
Not in that context. No, you're just using the algebraic expression to substitute out the intermediate.
Then it's just like being tapped into the rate constant.
The rate law. So when KEQ was used and introduced in Unit 5, it was purely an algebraic manipulation. Now we're introducing it as its own numerical value with weight. So the second thing to consider that's kind of a bit of a limit is, unlike Unit 5, okay, Unit 5 little k, I don't know how to do little k. What's the symbol for uncapital K? Little k, unlike rate law, this is the rate law constant, little k, that is used to compare reactions. Okay. We cannot reliably compare KEQ values between different reactions, with different reactions. So basically, the KEQ is not helpful when looking at two different reactions and being like, you can't really draw conclusive ideas from that. Like my KEQ is 7 for this reaction. My KEQ for this reaction is 8. It's like, great. Both seem to favor the product. As far as which one's working which way between the two of them, you can't make that conclusion. You can't say, oh, reaction B is moving faster than reaction A. That doesn't work. You can only make comparisons within the same reaction, and then identify generally where there's a favoring. Yes, Jaden? It's reaction specific. Yes. Little k is also reaction specific, but you can still draw conclusions like, hey, this reaction, because it's got a bigger k rate law constant, is moving faster than this other reaction, generically speaking. You cannot do the same thing here with big K. Big K does not do that.
You wouldn't even be able to compare for the same type of reaction with different concentrations.
Well, if it's the exact same reaction with different concentrations, then you can compare. But if it's like two different single displacements with different compounds, no, you cannot compare. So how, with the small k, we can compare because it's specific to one direction of the reaction going, and it's specific to the kinetics. Equilibrium is an adjacent to kinetics. It's based off kinetics, but it really focuses on ratio.
So with big K, I can compare like.
You cannot compare.
But like two different beakers of the same
reaction. Yes, you can compare two different beakers of the same reaction, and you can identify at what point in finding equilibrium they are. Yes.
What do you mean by compare? Like how exactly do we compare it?
I am faster than you. You are faster than me. Like that kind of compare?
Doesn't the equilibrium constant refer more to relative?
Exactly. That's why we're saying we really can't use it. So how to change KEQ? The only way you can change KEQ is to change the temperature. So otherwise, simply adding a catalyst speeds up both directions, which means the product and reactant concentration will remain the same, which means the ratio remains the same. Temperature is the only factor that actually changes the ratio between product and reactant that would be reflected in the KEQ, and that is all I'm going to say. Just remember that. It's a common MCQ, okay? So, quick check. Go ahead and try filling out this quick check and these KEQ expressions. Try writing them out. For this problem. So children, I need you to shut up. Okay. So for this question, that's right, parents. Sometimes kids need to hear that too. Just kidding. Your parents hear this in the background sometimes. I've had several parents tell me, like, we've heard you in the background. You're pretty funny, but you talk really fast. I'm like, yeah. Considering the following equilibrium, what direction will the reaction shift if some ammonia is added? Say what direction? Toward if I add ammonia. Products. Okay, toward product. I'm going to make more products. That is according to Le Chatelier's principle, the equation above. If I increase ammonia, I have way too much reactant, so my reaction is going to try to respond by using up, by producing more product. Okay, B, how will this affect the equilibrium constant? It won't, because only temperature can change the ratio to actually create a KEQ reflected change. Consider the following equilibrium. As temperature is decreased, we will shift toward what? Toward reactant. Excellent. So causing its percent yield to, okay, and its equilibrium constant to decrease because temperature does affect KEQ. It actually does change the ratio. Okay, considering the following equilibrium, KEQ is equal to 0.36. True or false? We know that reactants are favored in this reaction because KEQ is less than 1. True. Very nice. So write the KEQ expressions. Please tell me you got this. KEQ is equal to the concentration of H2O. Gas. It's not a liquid, so we do include it. Cubed. Okay. We do not include B2O3 because it's a solid. All over the reactants B2H6 and O2 cubed. Okay, KEQ here is going to be equal to H2O squared times Cl2 squared, products over reactants raised to their stoichiometric coefficient, HCl quadrupled, and what is that, quartetted? What do we call that when it's quartered? To the fourth?
Not quadrupled or quartet.
It's definitely not quartet.
Quartet. Does anyone want to be part of a quartet? I think it'd be cool. Okay, next one. KEQ is equal to HBr squared. All over, we will not include the liquid bromium because it's a liquid, but we will include the H2 gas. Okay, KEQ is equal to, oh my goodness, the reactant is solid. So all we have is product, calcium 2 plus and carbonate 2 minus. And by the way, this is a sneak peek into your lesson with Charlie on Friday. This is a special KEQ. For dissociation reactions, we actually give it a subcategory called KSP because there is no reactant, which means there is no ratio anymore. Now it's all multiplication, which means some of our principles of KEQ do change slightly for a dissociation-based reaction. Okay, but that's a sneak peek into Friday. So how do we do algebraic summation for determining the KEQ of a reaction given smaller reactions? All right, for a multi-step. So for example, let's say we have the following reaction. I'm ignoring you right now. Step 1, NO2 plus F2, okay, is an equilibrium producing NO2F and F. Step 2, okay, F and NO2 react to produce an equilibrium NO2F, giving me a sum of overall, wow, those boys are getting really loud back there. Overall 2 NO2, F2, and 2 NO2F. And if I told you my KEQ for equation 1 was X, and my KEQ for equation 2 was Z, what my overall KEQ for my overall reaction is going to be X times Z. So instead of adding like Hess's law and heat of formation values, now we're multiplying because again, KEQ is a fraction. It's a ratio. So the manipulations we do are adjusted to account for that. It's not a flat number produced through flat value. It is a ratio that we are now comparing to other reactants or reactions ratio. Here's the manipulations. If you reverse the reaction to get the overall, you're going to inverse the KEQ. To reverse is to now inverse because we don't really have positive and negative anymore. And if you reverse the reaction, you're flipping your product and reactant. So you're inversing your ratio according to the expression itself. Okay. If you multiply the reaction by a certain amount, you are now going to raise your KEQ times that multiple. No longer is it multiply, multiply. Now it's multiply by stoichiometry. Now that means it's going to affect my coefficient coefficients in my equilibrium. So that means it's going to affect my exponents, which is why when I manipulate the equation, my multiplication of the stoichiometric coefficients is reflected in an exponential value in the KEQ. Yes. This is like if I had a reaction and I had to multiply the whole thing to get it to cancel out to get the overall.
So it's not like you're doubling both the products and the reactants, it's just one side.
No, you're when you multiply a reaction, you are multiplying all the coefficients. So you multiply the entire ratio. But remember, our coefficients go in as exponents in this ratio. So that's why we're turning our multiple into an exponent. Okay, so when reactions are summed, you do KEQ 1 times KEQ 2 times KEQ 3 and so forth to get your overall KEQ for the overall reaction. So similar concept as what we've done previously through algebraic summation, but slightly different mathematical manipulations to, again, account for the ratio. Yes.
So let's say we have like reaction A and reaction B, both with one stoichiometric coefficient. We have 2 of A and 2 of B as an equivalent stoichiometric reaction. Wouldn't those have different KEQs even though they're the same reaction, just in different quantities?
But see, I'm talking about summation of a reaction to build one. You're talking about adjusting one reaction. I'm saying, how do I algebraically create and determine a KEQ for a reaction that I don't know, but I know other reactions that can be used to make it? Okay, so go ahead and try this quick check on your own for a couple minutes. So what you would do for this is to get this KEQ expression, you would see that this is the inverse or the reverse of the KEQ above. So it would be 1 over K because this is the reverse of the original reaction. It's reversed. For the KEQ below, you would see it was halved. So what you would do is you would multiply, sorry, not multiply, exponent square root your KEQ value because you have the original. Halved it. For the third one, you see that the KEQ is reversed and halved. So what it become is 1 over K to the half. That is your manipulations. Moving on. What if you're not at equilibrium? This is where we get Q quotient. Q quotient is the ratio between products and reactants not at equilibrium. So it's the exact same expression, just acknowledging a non-equilibrium status. Okay, not at equilibrium. So what's the connection between K and Q then? And please highlight the word not. Okay, so Q, by the way, would have the same expression though. It would be C raised to C, D raised to D, all over A raised to A, B raised to B, just not at equilibrium. So what we say is that we can use the relationship when a system is disturbed, the reaction will respond, okay, in a way that restores Q equal K, which is equilibrium. When Q equals K, you know you're at equilibrium. So this is how we numerically identify that we're not at equilibrium, is that the Q value, which is the exact same setup and expression, is not the K value. Okay?
Calculate them the exact same way. How would you get a different?
Because you would have a different measured mole amount of product versus mole amount of reactant. You would have different concentration. So if K is less than Q, that means the reaction will shift toward K reactants. Okay, to reestablish equilibrium. And the opposite is true. If K is greater than Q, that means there's way more product that needs to still be formed compared to what is currently formed. So you would say that we would shift toward product to reestablish equilibrium or to establish. Maybe you haven't even gotten to equilibrium yet, right? Maybe this is just the beginning of your reaction. So for the problem below, what we see is that Q is going to be SO3 2 all over SO2 squared times O2. And that's going to give us a partial pressure value. Remember here, we're using partial pressure with gases in general, we just use partial pressure as an indicator of concentration. And sometimes what we do is write Q little p to represent partial pressure as concentration, indicative of concentration for gas reaction. It would be 0.12 squared all over 0.057 squared times 0.057. And you would get a value of 78 for Q. Our K is 85 as given by the problem. K is equal to 85. So Q is less than K, which means our reaction will shift toward K product. So don't forget with partial pressure gas reactions, we use for gas-phase reactions, we use partial pressure as equivalent to concentration. Okay, so last thing I want to mention, I know I'm moving really fast. I do apologize. Tomorrow we'll warm up with these problems. These will be warm up. Okay. All right. When there is only one chemical species on the reactant or product side, we call it complete alleviation because there's literally only, like you either fix it or you don't. If there's one reactant involved, we call it a complete alleviation. If there's more than one reactant, more than one chemical species, okay, we call any shift a partial alleviation because it doesn't require all chemical species to change. In order to restore equilibrium. So that's the end of that. We'll also warm up with this tomorrow. And these will actually become some of your favorite questions because it's just, again, expression working. It's not crazy concept, hopefully. And if you start saying it out loud, the meaning, I promise it will make more sense. If you keep it in your head, though, it won't. Hear yourself say what it means, and that will make it clear. All right, guys, good work.